This video presents the paper entitled Analysis of Humanoid Body Joint Torques During Overhead Work with a Passive Exoskeleton. This work has been published in IEEE Transactions on Human-Machine System. Overhead work is classified as one of the major risk factors for the onset of shoulder work-related musculoskeletal disorders and muscle fatigue. Upper limb exoskeletons can be used to assist workers during the execution of industrial tasks to help workers and prevent such disorders. The lack of a quantitative metric for assessing an exoskeleton assistive support has been the engine for this paper analysis. The paper provides a solution to this challenge by proposing an analysis of the whole body kinematics and dynamics of the human during the execution of a typical overhead task to quantify the assistive support given by the exoskeleton. In particular, the paper contributions are the analysis of the whole body effects of a passive upper limb exoskeleton at the joint torque level, the definition of a validation metric to assess the exoskeleton performance, and the definition of a tool to provide the real-time estimation of the human kinematics and joint torques to be exploitable for the exoskeleton control optimization. The paper code and human models are publicly available on GitHub repositories. The paper dataset is stored on the Zenodo platform. Let's start with the background. The human body has been modeled as a rigid multibody system with 49 links connected by joints of 1 DOF each. The result consists in a URDF model scalable with the subject, whose inertial properties are obtained by combining anthropometric literature and measurements. The human is conceived as a floating-based dynamic system. The system configuration space Q embeds the pose of the base frame with respect to the inertial frame, and the joint position vector capturing the topology of the system. The velocity of the system nu is represented by the velocity of the base frame with respect to the inertial frame, and the joint velocities vector. Tau represents the joint torques, and Fx represents the external wrenches acting on the links. The floating base whole body kinematics and joint torque estimation is performed via a probabilistic approach with a stack of tasks maximum a posteriori estimator. The dynamics equation of the system can be properly arranged in a matrix compact form, and we consider to solve this new system in the unknown variable d that contains several quantities both for the links and the joints. Under the Gaussian assumption, the algorithm maximizes the probability of d given the set of measurements y, but the vector of our known variable d contains both the estimation of the external forces and the joint torques. The stack of tasks variant solves the estimation problem by decoupling the joint torques estimation from that of the external wrenches. This formulation is pivotal in computing the non-collocated wrench estimation. In details, the variant solves the problem as a stack of two tasks. The first high-priority task solves the system of the human external dynamics, exploiting the human centroidal momentum, whose time derivative is given by the sum of the external wrenches acting on the human whole body system. The main output of this task is the estimation of the external wrenches that is injected into task 2. The second low-priority task solves the system of the human whole body internal dynamics. The main output of this task is the estimation of the joint torques. If you are interested in knowing more about the stack of task approach for human dynamics estimation, do not hesitate to take a look at the associated paper. For the experimental setup, 12 novice healthy subjects have been equipped with the following wearable devices. For some specific trials, with an upper limb passive exoskeleton called PAEXO, provided by Autobock. With a motion tracking wearable IMU-based system provided by Xsense, and with a pair of sensorized shoes equipped with force torque sensors developed at IIT. The experimental protocol has been conceived to mimic a typical overhead working condition. Participants keep their left hand attached to a screen frame horizontally positioned on top of their heads. The right hand grips a drill and their feet were attached to the ground. The task is here to move the drill as fast as possible from a starting point to a target showed on the screen. Each session lasts 5 blocks and it is composed of 24 pointing movements. Each subject performs the task without the exoskeleton and with the exoskeleton. We use our pipeline for the estimation of the participants' kinematics and to perform a joint torque analysis for both the conditions. The difference between the two concerns the inputs in the measurement vector, especially for the condition with the exoskeleton, where the exoskeleton external wrenches are taken into account. For the PAEXO external wrenches, we considered a support force for the left upper arm, a force that is transferred to the pelvis, and a support force for right upper arm. The figure shows the raw PAEXO forces across 5 blocks at the intersubject level, the whole 12-subject dataset. Subject's posture for block 5 requires a PAEXO maximum support at the arms, and this corresponds to an increase of transferred forces at the pelvis. The figure shows a whole body reduction of the overall normalized joint effort due to the exoskeleton assistive support across 5 blocks. The support is 66% in the block 1 and reaches a higher value for block 3. A statistical analysis is computed here for the intersubject normalized whole-body joint torque norm, along with the sessions across 5 blocks. The two-way ANOVA is performed with 2 fixed factors, the sessions and the blocks, and with subjects entered as a random factor. The figure shows the evolution of the normalized torque norm across the blocks. The ANOVA reveals a significant effect of the session factor on the torque estimation. Conversely, the blocks do not affect the estimation at all. Here it is shown the difference between the mean of the intersubject torques computed with and without the exoskeleton for the head, torso, and arms. Bar plots quantify the magnitude of the effort reduction, green bars, and the effort increase, red bars, in performing the task with the exoskeleton. The presence of the exoskeleton reduces articular stresses at the upper body, shoulders, and torso. Further, the presence of the exoskeleton compensates the upper body reduction with a general increment of the stress at the legs. The internal forces are so intuitively transferred to the lower body. Simulation compares here the estimation of the human whole body kinematics and dynamics without and with wearing the exoskeleton. It denotes the decrease of the joint torque's magnitude at the upper body, the compensation of torque's estimation in the lower body, passing from the session without the exoskeleton to the session where the subject is assisted with PAEXO. Then, the paper conclusions are the definition of a quantitative metric to assess the assistance provided by an upper limb exoskeleton, the implementation of a framework for both the real acquisitions and estimations. Further, this paper highlights the importance of a control algorithm able to compensate for the effort joint torques distribution in the whole body. This study paves the way for the next challenging milestone, such as the optimization of the human joint torques via adaptive exoskeleton control. The work has been supported and funded by the Horizon 2020 NE project. Thanks for watching this video.